let us look at some basics of linear algebra. We begin with defining the inner product. So if you are given vectors x and y, so let's say that x and y are in Rn, then the inner product between x and y can be defined as x transpose y. So the another way of saying the same thing is that you are summing I equal to 1 to n xi yi. So this is like entry-wise summation, entry-wise multiplication, and then summation. Using this inner product, it is possible to define the Euclidean norm, right? So the Euclidean norm of x, so norm square of x is given by inner product of x with itself, right? Or another way of writing it is as x transpose x, right? And another way of writing the same thing is I equal to 1 to n xi square, right? So these are all for real vectors. Related concept in this context is that of the Cauchy-Schwarz inequality. So the Cauchy-Schwarz inequality takes the form, the Cauchy-Schwarz inequality takes the form x comma y less than equal to norm of x times norm of y. And the other side is that it is greater than equal to minus norm of x times norm of y. So both sides are there. Sometimes people get confused about the greater than equal to side, but both sides are there, right? And when does the inequality here become an equality? So when is this an equality? So this is an equality if and only if x is of the form alpha times y. So if x and y are vectors, then alpha is a scalar, right? So in that case, it is a equality. So here alpha has to be a scalar. So whenever the vector x is a scalar multiple of the vector y, then it is an equality. So the Cauchy-Schwarz inequality and the definition of the norm and the inner product gives us an idea of defining the angle between the two vectors. Specifically, we have that if x and y are both non-zero, so the angle between x and y can only be found if they are non-zero, otherwise the definition would not make sense. Then the angle between x and y, theta, is given by cosine inverse of x comma y inner product divided by norm of x times norm of y, right? And obviously the x and y are orthogonal. So x and y are orthogonal if x comma y is 0. So orthogonal means x and y are 90 degrees to each other. So this 90-degree concept is valid for n-dimensional spaces when x and y are n-dimensional, and they are orthogonal if x and y, the inner product, is equal to 0. The inner product, norms, and the Cauchy-Schwarz inequality can similarly also be defined for matrices. So for the case of matrix, we can define the inner product between two matrices as trace of x transpose y. So you can just verify that this operation trace of x transpose y for two matrices which are of size m cross n. First of all, x transpose y is a valid product of matrices, and this evaluates to a double summation. So I is from 1 to n and j is from 1 to m xij yij, right? So this is also entry-wise multiplication of the matrices and then summation of all the result, right? So in general, x and y have to be same size for the inner product to be defined, and in the same way it is possible to define the norm, the Euclidean norm or the inner product norm for this inner product, which is given by x transpose x. right? Trace of X transpose X. Another way of denoting this is the XF square. So F stands for Frobenius norm. Right? And as you can guess from here, this can also be evaluated as Xij square, summation over I and j Xij square. Sometimes we will define these quantities for symmetric matrices. So generally I will denote Sn as the set of all symmetric matrices of size n cross n, right, where X is equal to X transpose. So this is the set of all symmetric matrices.